In this Vertex 2 example, we have a Xilinx 18V512 PROM and a 44-pin VQ package, and we have a 2V40 FPGA and a 256-pin FPGA package. To run Universal Scan, you just place the two parts on the screen, add a port, hit scan, and instantly you see what every single pin on every part in the scan chain is doing in real time. Down here we've added 4 virtual LEDs to monitor the input buffers of the clock signals on the FPGA design. So at a glance, we can see that 2 of the 4 clocks are definitely connected to the pins under the BGA. The other 2 are not actually populated on the board, so that works out fine. Remember, Universal Scan only scans the parts at about a 10 Hz rate, so you're not going to see a 200 MHz clock. What you will see is the blinking pin or virtual LED, which tells you that there's activity at that pin. And let's face it, most of the time when we put an oscilloscope probe on the pin of a part, all we want to know is if the pin is high, low, or toggling. That's what Universal Scan tells us. It's an activity indicator. It's quick, simple, and intuitive. Over here we've connected some virtual LEDs to the mode select pins on the FPGA. How many times has your customer wondered if those mode select pins are set correctly under a BGA, but he couldn't check it because he can't get access to the pins? Well, now with Universal Scan, you just hook up a virtual LED and you instantly see how the mode select pins are set. I'm going to reach over to this board and pop a jumper, and you can see immediately how the mode select pins are set on this particular design. Down here we have a virtual 7-segment display that's been connected to the pins on the Xilinx that are driving the 7-segment on the board. Here, if we see the virtual 7-segment display working, but we don't see the hardware working, we know that the pins on the Xilinx are doing what they're supposed to be doing, and we must have a hardware problem somewhere between the Xilinx and the 7-segment on the board. That's the beauty of Boundary Scan. It puts you right between the firmware inside the part and the hardware outside the part and lets you see where you need to go spend your time debugging. So just that quick, we know that the oscillators are connected, we know that the mode select pins are set correctly. Let's suppose for a moment that this design isn't configuring for some reason. Well, the next thing we would want to know is, are the configuration lines between these two parts connected? So over here we've connected some virtual switches and some virtual LEDs to those nets. Down here we have the FPGA clock and the done signal. We've tied these virtual switches to the buffers, the output buffer and the tri-state buffer in the FPGA, and we've put some virtual LEDs at the other end of the net on the input buffer of the PROM. To test that net, we just drop the FPGA into XTest, click past the warnings, and now simply by driving the output buffer on the FPGA, I can monitor the input buffer over on the PROM to see that yes, in fact, that net is connected. I can do the same thing on the done signal. So I've just done a continuity test out from under that BGA over to that PROM on those two signals. Now to test the DIN signal, or the data line, I need to flip that around. I'm going to put the FPGA back into sample preload, put the PROM in XTest, click past the warning, and now I can drive the signal from the PROM to the FPGA to test that net. So just that quick, we've done a very simple continuity test between those two devices, and we now know that that is not our problem. In a nutshell, that's all there is to it. You just drop the 3 parts on the screen, add a port, and hit scan. You then add virtual switches and LEDs, and now you can see and control every pin around every part in the JTAG chain, specifically those parts under the BGAs. And remember, this works whether the part is programmed or not. So now you can do all this testing on a board that just came from the factory with nothing but blank parts on it, and you no longer have to wait for firmware to be complete to test the BGA hardware continuity.